Okay. So I'm going to start off, I'm going to talk about a more general type for this function, basically taking a function and applying it twice. So first off, what do you think the type of this function is? And don't worry about sounding stupid. I'm the one standing up front, so everything's going to be pointed at me. None of your names are being recorded for this. So, anybody got an idea of what the type of this function is? Yeah?
Function t to t maps t to t.
Right you are. So here's a quote from Bartosz Iluski from his post Limits and Colimits. Suppose the compiler wants to infer the type of a function twice, which takes f and x and returns f of x. The most general substitution is obtained using a pullback. I won't go into the details because it's beyond the scope of this book and beyond the scope of this talk. But you can convince yourself that the result should be function from t to t, function t to t, which is exactly what we said. So I'm not going to get into what a pullback here is. And while the given type of twice is certainly the principal type given normal Haskell, the rank 2 types language extension makes it possible to give other different types to this function. Yeah. So what types does that make? Is anybody unfamiliar with language pragma in Haskell? Okay. So Haskell has a standard for the language. And then every once in a while, people say, hey, I've got this new idea for how the language could work. And rather than making a whole new compiler, they suggest it, and it gets added to the compiler, but not added by default. You can turn on a bunch of these options by using language pragma at the top of your file. Rank 2 types is one of those language pragma. So normal Haskell types are rank 1. So a signature such as A to B to A is a rank 1 type. There's an implicit quantification for all types A and B in front of this. And you can always float types from the right of an arrow. You can always float for all statements from the right of an arrow to the left and back again. So we could also write this type as for all A to for all B to A. So we can freely float these back and forth in a normal type. What we can't do, let me check my notes, make sure I'm getting this right, is float them out when they're contained in an argument. So if we have an argument that looks like this, for all A to A, and it returns an int, something like that, we can't take this for all and float it outside of this argument. So it adds another rank to the type. Rank 2 types just says, I want you to allow types of rank 2. There's a more general extension, rank n types, which says I want you to allow types of arbitrary rank.
Yeah. When you say it allows types of rank 2, do you mean that it allows you to bring it out of the arguments?
No, what it allows you to write this type down, which you can't do in normal Haskell. Like that is a type, but it's inexpressible without this extension.
Wait, so what would it say? What the compiler going to tell you what's going on? Error?
Oh,
you know you come across like I'm trying to do
it will say you need to enable the rank 2 or rank n types extension.
Okay, cool.
It's pretty helpful in that way. Okay. So if we have rank n types, we can start and create some other types for f of x to f of x, which I have to find a more succinct name for. Does anybody have any ideas off the top of their head for what those could be? It's okay, nobody does.
Well, the main constructors.
Sure, absolutely. So you could have it take a function from A for all A to maybe A, and it would return a function for all B, A to maybe B. And I'm saying that f of x has this type. Do you buy that this expression can have this type? That's one of my examples that I have in the slides, only slightly more general. Does this need to be larger? Can people in the back read it? Awesome. So for any A, if we have some sort of function that wraps that type A in some type constructor M, then we can, by applying this function twice, we can wrap some type in that function M, or in that type constructor M twice. We can similarly unwrap something from a type constructor twice. So if we have some type WA, we can unwrap it to get the A inside, and we can do that unwrapping twice to take a WWT to just a T. So if you've been doing Haskell for very long, this top example makes you think of monads. If you've been doing Haskell slightly longer, this next example makes you think of comonads. But you can do even weirder stuff. Like you can take something A and you can return A tupled with itself. And so you can take some type T and return essentially a 4 tuple of T just by applying F twice. I'd like to note that all these things actually compile in GHC. I've got my slides running through the compiler, which is a great little feature called Literate Haskell. If you ever have to do a presentation, I highly recommend you do it. So look up both. We've got something that takes some sort of environment and a function from A to B and returns the environment and B. And it returns an even more elaborate function. I don't even want to read that type because it goes off the screen. Double rotation is easier to see. We've got something that takes a type constructor that takes 3 type parameters and rotates the positions of the type parameters. So we originally had 0, 1, 2, and afterwards we've got 1, 2, 0. So by applying that rotation twice, we take 0, 1, 2 to 2, 1, 2, 0, 1. If we did it a third time, we'd end up where we were to start with. So there's all sorts of wacky types we can come up with that all have this same implementation. We can add more language pragma to get even more features. Constraint kinds lets us talk about constraints, which are the types created by type classes. Allow ambiguous types lets us talk about types without exactly specifying where they are when we're defining them, only specifying what they are when we're using them. And so we can say we're constraining some function twice, constraining some input twice. It's not very exciting, but it's different. So what is a more general type for fx to f of x that encompasses all of these things? It will be much more satisfying if we had a single type for all of these things. So what does it mean for two types to be different? Or, the same? Which is sort of a question we need to answer first. So normally in Haskell, when we're talking about type equality, we're using something called nominal equality. Nominal coming from nom for name, meaning the names of the types are equal. Int is nominally equal to int. Int is not nominally equal to char. Int is not nominally equal to any other fully specified type except int. Nominal equality is very simple, very strict. But we can have something where we have two types that look different but are unifiable. Two unifiable types often happen when you have parametric types. That's types with a type variable. So here we have the type tuple of int and some value, some type A. And here we have the type for some type constructor m of a function from char to b. Somewhat surprisingly, these two types are unifiable. By specializing either these types, we can get them to the same type. I don't know why that. Okay. That's a typo in the slides. I apologize. So int to A, if we substitute char to B for A, we get this type, tuple of int, char to B. If we substitute tuple of int for M, we get the same type. So we have this type into A, we have this type M of char to B, and they can both specialize to this common type, int char to B. I can't specialize this type to that type, and I can't specialize this type to that type, but since I can specialize both of them to the same type, I say that these two types are unifiable.
Is only int char B the unifiable specialization, or are both constructors unifiable equals? Are two types unifiable equals if any type would lead them to unify to the same type, or is it only
I think, so a good definition for unifiable is if there exists some type that they both specialize to,
okay,
then they're unifiable. It doesn't necessarily have to be unique.
Okay.
Any other questions before I plow ahead, even weirder stuff? By all means, stop me.
Is there a category theory interpretation of type unification?
Yes, lattices.
Okay. Got it.
Yeah.
Okay.
It's one word answer. So lattices are made out of partial orders. Partial orders are saying you have one way of comparing two things. That's a whole thing. I'm not going to get into it today, but there's some great reading that I can recommend afterwards. Okay. So what we really want is a type for f of x to f of x that can specialize to any other type for that expression. So this brings us to the notion of what is called in Haskell a principal type. Principal type is somewhat surprisingly the least general type that encompasses all the possible types for an expression.
I'm just trying to get that side of it. Yeah.
Sorry.
No problem.
Okay. So one nice thing about having a compiler, and specifically having GHC, is that we can compare types using GHC. We can say, do these two types unify? So earlier, we had this thing twice, which was just using the bog standard definition, the bog standard type for this expression, where it was just saying, A to A, to A to A. That's the type of twice. Constrained twice was that something we came up with earlier, and we can say twice can be specialized to the type of constrained twice and prove it using this expression. So our compiler goes through this statement and says, does this expression have this type? It's satisfied with yes. Yes, it does. So we can say that twice, the type of twice, can be specialized to the type of constrained twice. Can we go the other way? Can we say the type of constrained twice can be specialized to the type of twice? Initially, no. If we try just telling GHC, try this, see if you can take the type of constrained twice and make it the same as the type of twice, it will fail. It will say, I don't know what constraint you're talking about. And this is exactly the ambiguous types problem that we enabled back when we defined constraint twice. We allowed ambiguous types, but now we're suffering the consequences of GHC saying, these types are ambiguous, I don't know what you want. So one nice thing, though, about this error is that the solution is in the error itself. So the problem it's saying, it says, I can't deduce that T, some type T, is equivalent to A. So we can write anything infix in Haskell, including this, as a prefix expression, right? So 5 plus 2 is, if you take parens of plus 5, 2, right? You can juggle your expressions around. These two things are equivalent in Haskell, right? Everybody's seen this before. Yeah. We can do the same thing to this. We can say T is equal to A. Type T and A are equal types. Express this as equivalence to TA. But back when we talked about constrained twice, just one slide ago, we have the ability to give constrained twice some constraint, C. Wouldn't it be nice if we could give C the value equivalent to T? Then everything would fall out. We can do exactly that using yet another language extension. We can substitute equivalent to T for C using the type applications language extension, which says you can use an @ sign followed by a type to say, I want you to specialize the variable, the type variable that I am trying to figure out right now with this actual type. This resolves the ambiguity and lets us specify exactly what C is. So we're saying the constraint is equivalence to T, and now we can define twice using constraint twice. And all we're doing,
For the kind of this type application, is it type to constraint?
yes.
Okay, so what if you need to do it in the opposite order? So say like A was the first argument, and you can't curry it. Is there syntax for that?
Not built in, but we'll get to that.
Okay.
Prescient question.
So why couldn't you just declare that type one line above without bringing in some extension? Is that possible?
I'm sorry, could you ask that quick?
Do you not like declare the type constraint one line above without bringing in that extension? Without bringing the type?
I need some way to specify the ambiguous type of this expression.
Yeah, one line above. You couldn't do that. Or are you just bringing it in because you want to like make it look pretty all on one line?
I don't know how I would do it on one line above.
I don't know either. That's what I'm asking.
I don't think there's a way to do it separately. You might be able to muck about with proxies somewhat and separate defined expressions to get something like this. But this gives us part of this is in fact just me trying to be very clean and show you that this value and this value are equal. All I have to do is specify the type. All I have to do is lead the compiler in the right way. So in order to figure out what this more general type could be, I'm going to take a step back and talk about a more restricted function. And my restricted twice function takes for all a to a, and returns a function t to t. And it's implemented the same way as all the others. It's just that its argument is much more restricted than anything we've seen so far. Can anybody name me a value of type for all a to a?
Id?
Yep, ID. And that's pretty much the only non-bottom value of that type. So this is an extremely boring function. It can only be applied to ID. And it applies ID twice, which is the same as applying ID not. So it's effectively a delayed ID function. So it's an extremely boring function. Doesn't do anything useful, unlike everything I've been talking about tonight, which is extremely useful and applicable to all sorts of work. That was sarcasm.
Would you be able to invert and then revert back to original state? And that would be the function applied twice? Like invert twice to get the original back?
So the reason that doesn't work for this particular function is that we can't define inversion for every single type.
Okay.
The only function that's defined for every single type is ID. Like we can define inversion for integers as negation, but we can't define inversion for strings. So
reverse a string. But
okay.
I mean as if it's
yeah. Yeah. But you start getting so we could do restricted twice using twice. So the type of twice is unifiable with the type of restricted twice. And if we define a new constraint called any, which is satisfied by every single type, then we can unify the types of constrained twice with the types of restricted twice. We can even, if we do some fancy wrapping and unwrapping, use double wrap and double unwrap, which were these take something and wrap it in a type constructor twice, or take something that's wrapped in a type constructor and unwrap it twice, and use those to implement restricted twice. Although we have to do all this bookkeeping in terms of actually unwrapping and wrapping things. And that's kind of a pain. If any of you have heard of coercible, let's get past this, but it still doesn't give us a pure sort of type level solution, which is what we've been working towards so far. What if we could skip the wrapping and unwrapping? So what if we had a type synonym is, where is of A just gives you the type A, wouldn't it be great if we could just wrap and unwrap is? That would be nice, but we can't do that. We can't use a type synonym that way. We can't say double wrap is because Haskell doesn't let us. GHC says the type synonym should have one argument. You haven't given me an argument, so I can't use it. So we seem to have an issue here. We want to be able to use this without wrapping and unwrapping because using actual type constructors makes us actually wrap and unwrap stuff. But we can't use type synonyms because they have to be saturated. They have to be past all their arguments. So this seems like an unsurmountable limitation. But it can be overcome using something called defunctionalization. So we have two sorts. I don't want to use types and I don't want to use kinds. We have two varieties, because sorts is like the types of kinds. Two varieties of type level functions. We have type synonyms, which must be saturated. They must be used with all their arguments, but they can resolve to types of any kind. So string is a synonym of list of char. Anything defined with the type keyword is a type synonym. Type constructors, they don't have to be saturated. You can pass them around willy-nilly. But eventually, they must resolve to some type of kind star, also known as type, kind, type, capital T. So, if you have, how many of you have ever used a monad transformer? Yeah. So monad transformers, you get to pass around which monad you're transforming, and you don't have to have it fully saturated. You can say, accept T of string is your error type, and then M, where M is your monad type. And it doesn't have to be saturated as M of A, it's just M floating around. So it could be IO, it could be maybe, it could be anything. That's what I'm not blocking. Sorry. So defunctionalization gives us the best of both worlds, but it's kind of a hack. We use a type constructor as a type level function identifier. So this identifier is something that we can pass around unsaturated willy-nilly. And then we match that identifier to an actual implementation, which gives us a type of any kind using a type family. So I'm going to start off by defining a kind for type level functions, for identifiers of type level functions. And I'm just going to call it dash dash greater than, because it looks sort of like a function arrow, just with an extra dash. And this is how I'm defining it. And what's interesting is that this definition isn't interesting. This definition is all perfectly arbitrary. All that's really important is that it mentions A and B, and it eventually ends in type. I could do all sorts of things for this. I could say it's A to B to type. I could say it's A to A to A to A to B to type. It doesn't matter. We're never actually going to use a value of this type. We just need to make sure that it ends in type so that it can be used as a kind for type constructors. Similarly, we can define a type family for our implementations. I'm big on puns, so I'm going to name this type family $, because it's going to be our application type family. We're going to take identifiers on one side, and we're going to take I guess for you guys, it's going to be identifiers on one side, $, things that are being applied to, and it looks just like function application using $. So we take some type level function identifier from A to B, some type of type A, and we return some type of type B. It's an open type family, which means we get to define what its instances are later. So let's compare our new type level functions using defunctionalization with value level functions. So here I have a type level function that I'm calling capital ID from A to A. And its definition, type instance, ID of A is just A. Really, really easy. And comparing this with this very illegible lowercase ID from A to A, and ID of A equals to A. You guys see the syntactic similarities between the two of these? Despite the fact that this is thoroughly illegible. Let me see if I can make it there. So we similarly have a type const, which takes some type C, another type A, and returns a type C. So const of C applied to some type just returns C. Similarly, the value level const of C applied to something just returns C. So we get to do these same functions at the type level that previously we were doing at the value level. One particular type level function that's going to be handy to us is lift, which takes a normal type constructor from A to B and lifts it into a type level identifier. So using ID and lift, we can apply defunctionalization to the types of double wrap, double unwrap, constrained twice, and get them all looking similar, looking like they're all specializations of some other type. So we can replace M in double wrap with lift M applied to A. And we can replace just A with ID of A. We can replace W with lift of W. We can replace C with lift of C. And now we get these functions that look like something applied to A to something else applied to A, resolves to the first something applied to T, goes to the second something applied twice to T. We see down here it's the first thing applied twice to T. So this gets us all the way here, which is where I wanted to go in the first place. I'm going to make this bigger, because this is the one that actually matters. So here's a function I'm calling self-compose. It takes a constraint, an input, and output type function identifier. These are all type function identifiers. And some types of V and W. We take some function that has a constraint on U that takes the input of U to the output of U. And now we have our functions that say we have this constraint for V. We constrain the output of V to be the same as the input of W. And we have that same constraint on W. And we take the input of V to the output of W. And now we can take this definition and use it just with type application to specialize to all these other functions that we've defined. Double wrap, double unwrap, constrain twice. We unify this type with the type of this expression with the type of all these other expressions. So what we've arrived at is something that for all the different ways we've come up with of writing f of x to f of x, a single type that unifies with all of them. So, is this the principal type of f of x to f of x? Probably not. It's an awful ugly type. It requires a bunch of specialized stuff. Defunctionalization is not really part of core Haskell. It's a hack bolted on top. But it's certainly closer than A to A to A to A. It lets us unify with all these types that we couldn't unify that type with. One strong argument that this is not the actual type was given by Dave Fuhrer, who comes here regularly but is not here tonight. His objection was that you can't have quantifiers in the right-hand side of a type family instance. So I'm not going to even try to read the type of this out loud. I encourage you to come and look at the notes. But I, so far at least, am flummoxed with trying to write, come up with a way of unifying this type with the type of self-compose. Another suggestion that I got via Reddit was to look at Stephen Dolan's algebraic subtyping thesis, which is actually really interesting reading. And he comes up with a way of he talks a lot explicitly about the lattice of types and how we could work with the lattice of types differently. So if you are interested in reading more about the lattice of types, I highly recommend this paper. He said, in his terms, which is not legal Haskell now, we could rephrase the type of this as A to A intersection B to A to B.
When he says work with the lattice types differently, does he mean a different ordering, or more generally like a whole different like?
It's so he does his thing. He does his work using sublattices to compare things rather than subsets, and it provides for an easier way of talking about subtypes.
Yeah, sounds like topology.
Yeah, but it's more approachable than a lot of topological things I've read. That's it. Any questions, or if you guys want me to go back over anything that I talked about, please let me know.
I don't understand typing a whole lot, but would unification, and what's the other one you talked about?
Specialization?
Specialization, are those like joins and meets in the lattice of types?
Yes. So unification just means that two types have a common. Okay. I always get joins and meets confused. I came up with a mnemonic recently that helps me.
If you say it as, then
Yeah.
I can sort it out later.
Yeah.
I get it. It's one or the other, one direction, and you have to
Yeah.
figure it out. Yeah, I get it.
So what exactly, can you launch the rockets now? What's going on here? Like, what did I just observe?
You observed.
Master's thesis.
No.
Like what you're like typing away, you're like, man, I really wish I had this. And then you went down this rabbit hole and it took you like 2 weeks to come out of, and then you're like, did this feature?
So I went down this rabbit hole because I was reading this paper, and it said the principal type of this function is this, and I said, no, that's not the principal type of it because I've got all these counterexamples that it doesn't unify with.
At any point was it launching rockets?
No, this is Haskell. We don't launch the rockets until we hit I/O.
Job created the book. I mean, so what I'm saying is like, is there like, now that I have this double unwrapping of the types that go down, I can do this better?
I can talk more clearly about this a class of functions.
Like if I put
This-
a Sudoku on top of it, it would just solve it in one line.
So
Or is that not, am I coming at it from the wrong perspective?
I'd say if you're looking at this from what does this get me in the long run, I'd say this gets you an introduction to defunctionalization, how it can be used and how it can be useful, how you can use defunctionalization to generalize the types of things, and talk about the same thing in many different areas without repeating yourself.
What?
So
I'm kind of new to this, so like, I'm a child's mind. I think
So-
that's the question, so I'm just curious.
parameterization
Yeah.
gives us the power to say, I don't need to write a map function for lists of ints and lists of strings and lists of doubles. I can write one map function that works with all kinds of lists, right?
Two birds with one stone.
Right.
Yeah, but this is taking like generics to like the nth degree.
Yeah.
And so like when I'm writing like a language that doesn't have generics, I would get tired of like saying, man, I really wish I had this function. I don't want to write this function for integers to map over a list. I don't want to write this function that maps whatever over the list.
Right.
I really wish there was a higher generic. And
Right.
so I can imagine somebody like making an application to have the username, stopping new strings, and then also the objects. And
So
then how
this-
do I bring this in and be like, man, now I got this. I can just do like this one
So-
line of double mapping, and then I can just.
So Haskell's parameterization is all dependent on position. It's positional parameterization. It's not parameterization by, like, you don't name the different parameters and then get to specify which ones you know and which ones you don't know. You only get to do it by position. And it's convenient and it's quick, and it gives us a bunch of classes like functor and monad and things and a lot of useful abstractions, but it's also kind of ties your hands a little bit. One example that I was reading about earlier today was if you think about either is not just a monad on its last parameter, but if you could flip the parameters, it's also a monad on the first parameter. So using defunctionalization in the way that I've shown here gives you a way of talking more generally about things without depending strictly on position. Sort of a hack to work around it.
Do you mean like allowing like unification between like either T of A and either E of A? Or like when you're saying it allows you to bypass position.
So
Does it allow you to like write bind for either the left or the
we
right?
could write, so we could, can I change what I'm presenting, it's not presenting, I'm presenting, I'm going to present a window. Do I get to choose which window? No, I don't. Awesome. Yes.
By the way, just the fact that you imagined or you think about it, right? And you're stopped by the GHC because let's say the GHC doesn't implement this. What prevents you from implementing it? Just make a pull request or
It can't. Okay. What prevents me from implementing it? Part of it is that we don't have the language to talk about it.
which part?
You can't like express the idea with
Right.
like GXC's type systems.
Right.
Yeah, but I feel like this is like trying to describe God. Like what's going on here? Am I super organic or is it like
No.
doing the weeds of stuff?
No.
Or like, okay, physicists observe something and it's like, okay, the sun's doing this and plants are doing this, and you try and find the experiment something to that associates the observation of this into theory, right? Is this backwards? Going from theory, we have nothing to like hopefully find an experiment in real life that this can be useful for? I come from a different background, not Haskell.
Okay. I mean, I imagine I may someday find a real life example where I desperately need this feature.
It's cool. I mean, that's cool.
Yeah.
Yeah.
I don't have one right now. Haskell is not my day job. Haskell is what I do to unwind at home.
No, yeah, I get it.
Okay, so.
Could you implement this in Idris or something that's?
If I knew Idris, probably.
I'm not Idris, so people
I mean, a lot of what I've talked about here would be much easier in Agda or Idris or Kaf, because at least the one of those I know is Agda. The other two, I'm pretty sure it's also true that it's much easier to talk about type level functions without constraining yourself to just type constructors. Yeah.
I have no idea what that means.
So the defunctionalization trick was basically us taking a type level function and splitting it into an identifier and an implementation.
Right.
And the benefit of that was we can pass the identifier around because it's a type constructor. We're allowed to pass type constructors around. And we can have it resolved to an arbitrary type because type families are allowed to resolve to arbitrary types. And type constructors aren't. Type constructors can only resolve to parameterized types.
Can you describe this in formal mathematics? Let's go backwards. So like,
Okay.
Haskell's trying to map into math. So like,
I sort of wonder if maybe we should take this offline, and maybe you can show us this example, just because we need to get going sooner.
Yeah.
Probably. Yeah, almost 8. So.
Okay. So we can come up with our own monad class. I can type.
built that, was it you, Sam? You said you were building that level. Riley?
Live coding, always a joy.
I was thinking
So,
you could actually do it.
Just by saying.
It would be hard to work because it's such a small.
That doesn't give us much because we're applying M all the same places, doing all the same things. We would want to do something more like
So what would be like a one level above this? Like this seems like even Bartow's researcher type fellow.
Yeah.
He's playing with the idea, but he's like in the weeds. So what would be like one level? Okay, this is practical. We can launch rockets quickly with this.
I don't know what you're saying.
So one example is this type is more general. This type we have the large. Right. So say we have two different higher order functions. One that takes like what we our previous type for double application, and one that takes one of these other types as well, so like graphic in some format twice. Right? Now we have a more general, like, we can define this function at the top of what's more general type, and then pass it to either of those types of functions. Right? So we've done the same thing we always do. We have generic sort of parameterization, right? And we're now using the one definition for two purposes, for one purposes. Right? We made this more general.
Right.
We're generalizing in the hopes that we can reuse code.
Right.
Okay. Thank you all very much.
Sir.
Noah.
Okay, so possibly like you're rather going that twice for whatever reason.